Our next topic is stored procedures. Let's take a look at what the documentation from Postgres tells us about stored procedures. So we're going to talk about a particular language that's native to Postgres called pgSQL. That PL is a common prefix dating back quite a long ways and been used in different languages. It just stands for programming language, and it's a programming language for PostgreSQL. Clunky name, but that's where it comes from. The first thing to note here is that this is a procedural language. Now, when we're thinking about relational databases, it's a little unusual for us to think procedurally in some sense. When we make a query, for example, do a select statement, we know that behind the scenes, the database engine is doing a bunch of work that's trying to figure out how is it going to go and grab the results of this particular select statement. And we're going to talk in more detail about how that works in a few lectures. But that's not a procedure. We're not saying to the database, go out to this file and grab these records and compare them with these other things and run this function. We're saying, here's what we want to get back. You go ahead and figure out how to do that. So that's an example of what we'd call declarative programming. We're just specifying what we want to get back. We're trying to give the database an idea of the result that we want. We're just declaring that request to the database. A procedural language is more what we're used to thinking of in a programming context. So writing a C program or a Python program or a Java program, those are all examples of programming languages that support procedural programming, where you've got to tell the program exactly what steps to take to solve the problem, as opposed to just saying, hey, I want you to figure out what to do behind the scenes. So this is a little bit different, and it will feel a little familiar in that sense, that it's going to feel similar to writing a traditional program. We'll see that the pgSQL can be used to create functions. So if we want to add new functions to our database environment, and it also can be used for triggers, and that's actually going to be our next topic that we're going to talk about. And basically, a trigger is a procedural function that can be run in response to some action. So when somebody makes a change to the contents of a table in our database, we can configure it so that it runs a procedure in response to that. We'll unpack that in a lot more detail later on. It adds some control structures to SQL, so we'll see that we can do conditionals and looping and case statements and a variety of different things. Can perform essentially arbitrary computations, right? It's a Turing complete language, so we can compute pretty much whatever we need to. It also makes use of all of the user-defined types and functions and operators and other things that are part of the Postgres environment, so we can access all of the goodness that we've been used to using for declarative programming and using data. It can also be defined in such a way that it can be trusted by the server. Now, that's actually a little bit of a subtle point. You will see that we can also program Postgres using Python, for example, or C. But in those cases, we're sort of giving control over to an external language interpreter or compiled code, which isn't as trustworthy, right? The code might do some weird things with our data that Postgres has no notion of what's going on. On the other hand, when we write in pgSQL, we can trust that the database is not going to be adversely affected by the code that we write. So if we try to write some code in pgSQL and we, for example, try to violate a foreign key constraint or try to violate a primary key uniqueness constraint, Postgres, because it's sort of in charge of running that program, is going to prevent us from shooting ourselves in the foot that way. The documentation claims it's easy to use. You can be the judge of that. One of the things that is a little disappointing about programming languages that are built into databases for doing stored procedures and triggers is that they're kind of sort of clunky, and we'll see how that plays out. That said, there are a lot of advantages to using a stored procedure, not least of which is that the stored procedure, by its name, suggests that it's stored in the database. So we've talked on a couple of occasions about the notion that what we want to use in a way a database for is to kind of be a backstop against bad data, against unquality for our application. That in some very fundamental way, the database can ensure certain kinds of constraints and characteristics like primary key constraints, foreign key relationships, and other sorts of constraints that we've seen. So the good news about using a database kind of as the last best hope to make sure our data stays in good shape is kind of extended by this ability to define our own functions right inside the database. So when we write a stored procedure in Postgres, we're not writing it in a separate file necessarily and then having Postgres somehow call out to that separate file. We're actually writing it directly inside the database. So the database itself is responsible for hanging on to these stored procedures. That means that we have a one-stop shop to do any kind of additional processing, additional verification, additional validation located in the database itself. And that's going to make our system tend to be sort of more reliable, of higher quality, because we can ensure certain kinds of constraints are always going to be paid attention to, because the code isn't going to be reliant on some outside person, another programmer, making sure that something gets wired up properly. It's in the database in very much the same way that a primary key is in the database and is going to be observed and obeyed by the database itself. Why do we care? Here's some more justification for this idea of using stored procedures. So far, whenever we've made a request to the database, the SQL that we've issued to it, whether it's a select or an insert or an update or delete or a create table or whatever, every one of those statements is going to be executed individually by the relational database. So when we issue a command, say from DataGrip or some other database IDE or a command line client or something like that, we're doing multiple steps. We're sending a query to the server. Then we're waiting for execution of that script on the server, and we're going to see that that actually requires quite a lot of work, as I've alluded to just when talking about declarative programming. We're going to have to receive the response and process the result of those responses, and then we can go ahead and send more queries. So it's kind of a low performance kind of a proposition here. We've got to send a request, wait for that request to be compiled down into something that the database can actually do. It's got to go do it. It's got to collect the results. It's got to send those back. A lot of monkeying around to satisfy every single SQL statement that we've issued so far. As soon as we bring stored procedures into it, well, first of all, we get the power of a procedural language, right? So we kind of get the ease of use of SQL, and ease of use in the sense that we can just declare the results that we want to get back instead of having to tell the database in detail how to construct that result set. And there's quite a lot less overhead in communication going on. If we've defined the functionality that we want to have the database do in one spot inside the database itself, like I was talking about, then we're going to eliminate round trips back and forth between our client and our database server. So instead of having this kind of cycle that we talked about up here, where we're sending multiple queries to process results as we get them, for example, we can just define that processing once, put it in a stored procedure, and it's inside the database, such that when we make the top level request, that functionality is already wired into a stored procedure someplace. So we're eliminating these round trips. We don't have to marshal data. We don't have to marshaling is basically just encoding it for transmission across the network. We don't have to move it across the network, and we don't have to do these sort of multiple rounds of connection to the server in order to be able to do these things. So the bottom line is, in many cases, we're going to get a performance increase. So we're not only getting more reliable code because we're putting all of the functionality that we can in the database itself, but because it's already over there, we don't have to deal with these kinds of sources of overhead and can just do that computation in the database management system itself. All right, let's turn to the syntax of pgSQL. So here's a super simple high-level overview of this. Note that we're talking about a create command. So we know that create and alter and drop are commands that normally are thought of as being part of the data definition language portion of SQL, and that's the case here too. We're going to create some new things that live in the database, just like creating a table or whatever, except now we're going to create a function. So that's the way that Postgres refers to a stored procedure. So the statement is create function, and then there's a declaration of how the function is going to work, how we're going to invoke it essentially, the information that says what kind of type it's going to return back to us after the function executes, and then we give the definition itself. And again, we're going to use this little as keyword as kind of the following is the definition. Now, a weird thing, and I've kind of just put in a placeholder for the function body, but here's the weirdness associated with stored procedures, is that the procedure itself, the function body, the definition of the function, is given to SQL as a string. Now that's kind of a weird thing, right? When we're writing a program in other languages, we don't just put it all inside of a big string and then send that off to the compiler. We have a particular top-level syntax that we can use and IDEs know about and all that sort of thing. Much more sort of flexible and a standard approach to this. Because stored procedures, in a sense, were kind of bolted onto SQL after the fact, there was no general purpose portable mechanism for including stored procedures in SQL proper. So the designers decided to finesse that by just saying, let's make this a string. We'll pass that string over to the SQL server, and then it'll look inside that string and do whatever compiling and things it needs to do to be able to run it. So that turns out to be a source of some of the clunkiness attendant with writing stored procedures. And we'll see some ways that that's ameliorated in Postgres. The other thing that we're passing here as a required portion of this create function is to say which language are we going to use. So you can see here is pgSQL. We're telling it which language this particular function is written in. As I mentioned before, we can also program Postgres stored procedures using Python or C or Perl and some other languages. So we need to be able to tell the database server which language we're using. So the body of this function is a string literal. That obviously creates some issues for like escaping those quotes and that kind of stuff. And we're going to see that there's a mechanism that helps us get around those kinds of awkwardnesses called $quoting. So $quoting is a way to work around this awkwardness of having to embed our code inside of a string. A standard SQL string uses single quotes, and the single quotes and backslashes, if we want them to appear as themselves inside of that string, they have to be doubled. So that's a kind of a unusual way to do it compared to some other programming languages. It tends to be something that's rather hard to read. And if we are forced to observe that convention inside of all of our stored procedures, anytime we wanted to use a backslash, say in a regular expression, or anytime we wanted to use quotes inside the procedure, we'd have to double them, which is going to just make it really hard to read and understand and get correct. So Postgres has this thing called a $quoted string. So it's a new syntax to indicate a string that is different from any other kind of string that's in SQL itself, so that we can use it as a delimiter around a procedure without it having any kind of a collision with the contents of the definition of that function. So what does this look like? So the $quoted string uses this syntax, a $, an optional tag, and another $, as the opening quote mark. Then we can have an arbitrary sequence of characters. In our case, that's going to be the body of our stored procedure. And within that arbitrary sequence of characters, the top-level parser for SQL isn't going to pay any attention. So if we have quotes and backslashes and stuff inside that body, the parser isn't going to pay any attention because it's looking for the corresponding close quote, if you will, that uses this same $quoting mechanism. So after that arbitrary sequence of characters, we want to see another $, that same tag, if we used one, and a second $. One thing to note is that this is not standard SQL. It's a Postgres kind of a thing. And here's a couple of examples. So in the first case, we've got double $, before and after a string, Diane's horses. Now notice that there's a quote mark inside of here, which if we had used ordinary SQL single quotes, we would have had to double in order to be able to include that in the body of this string. But because we're using $quoting, $, before and after that string, it's escaping anything else inside of there. Now that's the case where we have used no tag, right? This tag is optional. We don't have to use it, but we can, if we choose to, for example, to allow us to nest even the $quoting mechanism, we can, instead of just using the $, we can use this tag. So some tag inside of here begins the $quoted string. We can use the ordinary quote mark inside of there, and then it's going to be terminated by the dollar quoted string using the same tag. So these two things end up being paired up as the open and closing quote, dollar quotes, around that string Diane's horses. And notice that none of the characters that are inside that need to be quoted, because we have this notion that we've got an arbitrary sequence of characters between the two dollar quoted delimiters. We can choose those tags, which again allow us to do some nesting here, for example. So here's an example of a function that starts out with a dollar quoted string function that has no significance other than just an arbitrary tag inside the dollar signs, and it ends with a dollar quote string that looks exactly the same. So the body of the function is from this begin to the end. And we're going to talk more detail about what the syntax looks like there. But now we've got something else going on in here where we want to use some backslashes. So I'm checking to this is basically an operator that says do a regular expression pattern match from this parameter against this particular regular expression, right? So it's a character class that contains a bunch of white space characters, tab, return, new line, vertical tab. Rather than having to double these guys up to allow them to occur inside of this function, what we're going to do is use a second set of dollar quotes to make it simpler to encode the character class. So the $Q open and closing quotes is a nested dollar quote inside of this top level dollar quoted string that contains the overall function. So that's kind of the reason behind the idea of a tag appearing between the dollar signs, is you can nest these things and they're not going to collide with each other. Whereas if we only had like one syntax, just double dollars, for example, with no intermediate tag, then if we'd used double dollars here, we would have closed off those double dollars here, and then there would have been a syntax error as the SQL server tried to parse that stored procedure. So that's the way we kind of get around this rather painful choice that designers made to make stored procedures be a string. You use this kind of goofy looking delimiter to set off the function body. Let's take a look at our first actual stored procedure. So we've got create function, again the data definition language statement that's going to create a new stored procedure. We're creating a function called sales tax, sales underscore tax, and it's going to take a single parameter called subtotal, and that is a real value. Now notice that this is an ordinary Postgres data type. We could define a table that has a column that's defined to be type real, and the stored procedure syntax uses that same syntax that we use when we're doing a create table. The name of the column in the case of a create table, and then its type. In this case, we're giving it the name of a parameter and its type, but the same syntax is going to be used. We're going to return a real value as well. So that's just part of the standard create function syntax. And then we're going to use as to delimit the kind of declaration here from the definition of the function. And we're going to use the double dollars for dollar quoting for the body of the function. That red box around there is just an artifact of LaTeX formatting of these slides, so that has no significance. It's just double dollars. And this is a very simple function. It starts with a begin and ends with an end. You can see that there's a kind of, that implies a kind of a block structure to Postgres stored procedures, which is going to turn out to be true. And this particular procedure does very little. It takes that subtotal value and multiplies it times a standard tax rate and returns that value back to the caller. So some things to note about this. First of all, the keywords are not case sensitive, but this is kind of a typical way to write those stored procedures. I kind of prefer to make the keywords uppercase, but it's not required. Identifiers are converted to lowercase unless you quote them. Again, just something to be aware of. Don't get too bent out of shape about about that, just write your procedures as you might normally do. There's also some additional ideas here about commenting. So we can use standard SQL comments, which is just from a double dash to the end of the line. So if we wanted to put a comment in here, we could just say dash, dash, and then write some stuff in here, and that would all be considered a comment up to the end of that line. Or you can also use C-style block comments with slash star and star slash at the end of the comment, and this can go across multiple lines, whereas the standard SQL comment is just the same line. So that's how we create a function, and we can also, because of the way that the data definition language in SQL works, we can also alter those functions and we can get rid of them. So if I want to drop a function, I just say drop function, and then I have to say the name of the function I'm dropping as well as the signature of the argument list. We'll see that stored procedures can actually be polymorphic. They can take different forms, they can have different argument lists, and so we've got to tell the database which of the possible multiple definitions of this sales tax function might have been in view when we want to delete something. Now let's use that function in a query. So here's a hypothetical query against some kind of a commerce database, and we're going to select a payment ID, a payment amount, and then we're going to calculate some sales tax and add that to the payment amount in order to display a total. And we're going to select from this payment table, and limit 5 is just to keep everything on the slide. So here's our payment ID, here's the amount of the payment, and then here's the total charge. And you can see that that's computed from this expression. So we're going to take the amount plus the sales tax of the amount. So here's where we're invoking our stored procedure, passing in the amount value for this particular row. That's going to multiply times 6% and then add that to the original amount. And we're wrapping this up in a toChar, which we've seen before is the standard function to use to format the output in a particular fashion. So this is going to give us 2 digits, the decimal point, and 2 digits. And we're also using an as here to give this a more friendly alias instead of seeing that whole expression showing up in the output table. So you can see that each of these amounts has been increased by 6% because that's how we're calculating this total column. So let's take a look at some of the details of pgSQL. First of all, as I mentioned, it's a block structured language, and it uses this very verbose syntax for declaring blocks. So instead of curly braces like we would see in a language like C or C++ or Java or JavaScript, pgSQL uses begin and end to delimit a block. This general syntax then is that we've got an optional label, and that's only going to be used for an exit statement. Basically, it allows you to exit an enclosing block more conveniently. And then any of the statements that are inside of here can itself be a subblock. We can use that to group things logically, to have different scopes and localization for local variables and that kind of thing. So it behaves like most block structured languages that you're familiar with. It just uses this more verbose syntax. Let's talk about how we pass parameters to a pgSQL function. Here's another create function statement. This is a little bit different. We've got create function and then this get sum. It's just going to basically add 2 numbers together, so it's not very interesting. But I wanted to point out here also that there's a variant of the create function syntax that allows you to redefine a function if it's already been defined. Remember that these functions are going to be stored persistently in the database so that we can use them from any application that might have access to this particular function. And because it's stored in the database, you need to be able to update it if it needs to be changed. So one way to do that would be to do a drop function to get rid of the function, which we saw an example of a little bit ago. Or we can use this or replace syntax that says either create it if it's not there yet, or if there is a function that has this signature, go ahead and replace it with this definition. This function getSum, it's just going to return the sum of 2 values, and you can see here that the parameter list follows the pattern that we looked at before, where we've got the name of the parameter and then the data type. But there's an additional option here you can use to say that this is a parameter that's going to provide a value into the function, and that's the default. So in this case of parameter b, we don't have to put anything there to say that we want this to be an input parameter. And then we can still say that it's going to return some value, it's going to return a numeric value, and then here's the signal that we're about to define the function. We're using the dollar quoting mechanism, and then inside of here we've got just a block that has just a single return statement that gives us the sum of the two parameters that come in. And then of course we're always going to include this language keyword to tell the database which of the various languages that are supported we're using for this particular function. And then to invoke this, I've mentioned a couple times that the select statement is quite generic in terms of the kinds of expressions that it will take. So in this case, we're actually just using select to execute this function, passing it 17 and 42 as the arguments for a and b, and then the result we get back is going to be a table, as you won't be surprised to find out, that just has a single value of the sum of those two input parameters. One thing to note in this function declaration is that we're explicitly returning a value back from the function that then is being provided as the value that's shown in the select statement's output. We don't have to have that returns clause, however. We can get values out of a function by using an out parameter, as we've got going on here. So here's a little function called high-low, and what it's going to do is take three arguments called a, b, and c, and again, because we're not giving any particular decoration, those default to be input parameters. And you can see that what they're going to do inside the function is call this function called greatest on those three values and least on those three values. So greatest and least are just built-in functions that take a list of arguments and return either the largest or the smallest numeric value. And then those are being assigned to two variables here called high and low. And the language uses this kind of goofy walrus syntax for the assignment operator, a colon equals. That's actually got kind of a long and storied history in computer science. The language Pascal, which was a big deal back in the 70s and 80s, used that kind of syntax primarily because it just sort of looks weird to see an assignment statement in a program. If you say something like a equals a plus 1, we're sort of familiar with that as an operation that's going to increment a. But if you just sort of look at it mathematically, it's completely bogus because a doesn't equal a plus 1, no matter what a is. This is the assignment statement, a little bit different syntax, but does the same job. Now what we're assigning to are two additional parameters that we're passing in as the values in this function, called high and low, and they're both numeric values, and they're declared to be out parameters, which means that when the function returns, those two values are going to be made available as the output of this function. So we do this assignment inside the main block of the function, and then when we invoke it, so calling this with high-low and passing in 10, 20, and 30, we can see that the output from that query tells us that high has the value 30, of course, because it's the greatest, and low has the value 10 because it's the smallest. Note also that the way we call this is a little bit different in that we're invoking high-low from inside of the from clause because it's going to return a tabular value, and then we're selecting both of the columns essentially from that function with the star here. We could also have said select high from high-low, or select low from high-low, or select low comma high, and all those things should work to give us the appropriate output here in the result set. So we can define parameters that are going to be input to a function. We can define them that are going to be output from a function. We can also have parameters that are going to go both directions, called in-out parameters. And you can see here I've got a little function called square that takes an input parameter or an in-out parameter called a, and then it's going to actually also return the result of a in the block that defines the function. So I'm just taking a and assigning it to be a times a. Again, that looks a little nicer to see the little walrus operator there because a does not equal to a, does not equal a times a in general. So this assignment statement makes it a little bit clearer what's going on. And then we're going to call this, again, kind of a similar way to the way we called the first example, by just selecting the single value that comes back from that function in this case. I mentioned before that pgSQL allows us to do function overloading, so we can have multiple functions that have the same function name as long as they have different argument lists. So here's an example of that, and we're also going to talk about some of the other things that we can do inside the function body. So again, create a replace function. We're going to define a function called getRentalDuration. That's going to take the ID of a customer. Now in our database, our DVD rental database, those customer IDs are integers, so we need to define the parameter that's going to be used for a query using that column to have the matching type. And this is going to return an integer as well. So first thing we're going to do here is declare a local variable. And we saw back here when we were looking at the basic syntax for the block structure of pgSQL that we can have optional declarations here. So this is our first example of that, where we're going to declare a variable called rental duration, and again it's got to have a type consistent with the types of SQL. So we're going to declare that value, and now we're going to show how to assign to that variable. And we're going to do that instead of using an assignment statement like we've seen back here. We're going to actually assign a value to that variable from a database query. So let's look at the query itself here. Look at some of the familiar things first. We're doing a select, and we're selecting from the rental table, and I want to get the information from that rental table where the customer ID, and that's the column name in the rental table, is equal to P customer ID, and that's the name of the parameter here. Now that leading P underscore is just a convention that makes it a little easier to distinguish a parameter that's being passed into the function from a column that's got the same name in a table that we're manipulating. So we're going to fish out rentals that come from that particular customer that we're passing information, or that we're passing into this function. Now what are we going to do with that? Well, first of all, we're going to select into that rental duration variable. So this is new syntax that allows us to take the result of a query and assign it to the variable that we've declared earlier on. What is this query going to assign to that? Well, there's a little bit of new stuff going on here. In particular, we're taking the return date from the rental table for each of the rows that are coming back from this query and subtracting off the rental date, which is going to give us sort of a delta in between those two times. What we're trying to do is come up with the rental duration in days, and we're going to do that using this extract operator, which in this particular case is being used to extract just the day from this time delta, and that's going to give us the total number of days for this particular rental. Now notice we're also doing an aggregation function. We're summing up the duration of each of the rentals that come back from the query, where the customer ID associated with that rental matches the customer ID that we're passing in as the only argument or the only parameter to this function. So the result is going to give us the total number of days that P customer ID had a rental video checked out, or rental DVD. And then we can call that, just like before, with a select statement. I'm passing in a customer ID, and we can see here that the value we get back says, well, this customer has, in total, rented DVDs over 90 days. Now, the heading of the slide suggests that we're trying to illustrate function overloading, so I'm going to define another function called getRentalDuration, but it's going to have a different signature, different parameters. So here's another variant of this function, still called getRentalDuration. It takes a customer ID as its first argument, but it has a second argument that's of type date. And it's going to do a very similar thing, except there's a new conjunct in the where clause that says, in addition to giving me the values for this particular customer, tell me about the rentals that this customer has made since that particular date. So the rental date greater than or equal to P from date is going to just give me those recent rentals. The rest of the function is all the same in terms of extracting the total number of days per rental and summing that up using the aggregation function and giving the value back. But you can see now we've got two functions called getRentalDuration, one that just takes the customer ID, and this one which takes the customer ID and then is followed by the from date that we want to use. Notice the syntax here for the from date. This is the it's called the ISO 8601 format for dates. It uses the year followed by the month followed by the date. And that's a pretty typical representation for dates in many database management systems. I'm actually pretty fond of that syntax, not least of which because if you use it in a file, you can just sort that file and it will come out sorted by date. As long as you use four-letter day, or four-letter year, two-letter month, two-letter day, it sorts lexicographically in a way that's also chronologically, which is really handy. So we can see the output from here just says, well, that same customer since July 1st of 2005 only rented DVDs for 71 days instead of 90, which would have been the all-time history for that particular customer ID. We can also return a table from a function. So again, create or replace function, get film, and we're going to pass in a pattern. That is going to be a varchar, so that's just basically an arbitrary length string. And what it's going to do is return a table. So instead of having a scalar value as we've had before that returned in the form of a single cell table, we're going to return a bona fide table. So the table itself is defined here kind of dynamically in the function declaration. So we're going to return a table that consists of two columns, a film title that's a varchar and a film release here that's an integer. Now, that's essentially the same kind of syntax that you see when you do a create table statement when you're creating an actual table. So it's not surprising that the function uses a similar kind of syntax to define the form of a tabular value that's going to come back from this function. So how do we actually do that? Well, we're going to return a table in this case, and the syntax here is to say we're going to return a query, and the query is defined as a select statement, just like normal. We're going to select the title, and then we'll come back to this, but this is going to end up being the release here, from the film where the title is like p pattern, right? So again, this p underscore, just a convention that you can use if you want to indicate that that's a parameter to the function. So we're going to go to the film table in the actual database, and we're going to run this select statement and pick out the title and then this second crazy thing from film where the title of the film matches that pattern. So you could pass in a pattern that had letters, numbers, the percent sign, wildcard, the question mark, wildcard, and so forth, and what you'll get back is a two-column table containing the title and the release year. Now, why is this what's going on here with the release year? Well, using another piece of syntax we haven't seen before that is, well, it's a cast operator. So it's the same sort of an idea as a cast in a language like C, where you prefix a return value or an assignment from one type to another, like casting a pointer, where you enclose the new type in parentheses. Here, we actually have verbose syntax to say, I want you to cast the release year from the database as an integer. You might wonder why we're going to all this trouble. Well, in the definition of the schema for the DVD rental film table, this release year is actually defined to be of type year, which carries with it a whole bunch of additional baggage having to do with dates and times. And what we're trying to give back from this function is a table that just has the title as a string and the year as an integer. So we're using this cast function to convert this from being a year to being just an ordinary integer. Let's take a look at how we are going to invoke this. Again, the function returns a table, so you won't be surprised to find it showing up in the from clause. The from clause normally names a table that's actually in the database. In this particular case, we're calling a function that returns a table, so we could put it right in the from clause itself. And in this case, I'm just selecting star, but we could also do any expression that we wanted to that made sense in the select statement if I only wanted to get the film title and not the film release year. I don't know why I would be calling that function if that was the case, but at any rate, the getFilm function takes as an argument a string that in this case is a pattern that says capital A, lowercase l, and then any other characters. The percent sign is that wildcard character. So that's going to be the value that's going to be assigned to p underscore pattern to be used in the like comparison in the where clause. And you can see that what comes back here is films whose titles start with AL, and then the corresponding release years, which is now an integer instead of the underlying year value, which is in the database. As I mentioned, the pgSQL is a full-on Turing-complete programming language, so you can do all the things that you might expect to be able to do in a programming language, including iteration. And we'll see what the syntax is here in a second. So we're going to do a function called getFilm, and it's going to take a pattern that's going to be a varchar, a string, as well as a year, which is just an integer. And as the previous example, we're going to return a table that's going to have the same shape as what we saw before. It's going to have a film title and a film release year, and then we've got the as, and then just to remind you, we're using the dollar quoting syntax. We've only got one level of nested quotes, so we're just using $$ without any intermediate tag. We're going to define a variable in here that's going to be our iteration variable. And in this particular case, we're going to be iterating over the results of a query. And the way that we specify that as a sort of a generic type that just refers to sort of an arbitrary row from a query is to give that a type record. It's kind of an old-fashioned name for a row that comes back from a query, or a data record that comes out of a fixed format file or something like that. So it's pretty generic term, but we're going to use this var. Again, here's another kind of goofy syntactical choice to indicate that this is a variable that we've defined in here. You don't have to use that syntax if it seems unnecessary or arcane to you, but it's a convention. Now here's where the iteration takes place. So we've got a for loop. It's got a control variable, as most iterative constructs do, and we're going to loop over the value that's defined by this in. So the thing that we're looping over is going to be the result of a query, not surprising. And the query is pretty simple. It's just going to grab the title and the release year from the film table, where the title matches the p underscore pattern, and the release year has the value for p underscore year. So this getFilm function is used to say, I want to get all the films whose title matches this pattern that were released in this year. So the query is kind of uninteresting, but it is now being used as the data over which the for loop is going to iterate. So we're going to process each row from that query one at a time by assigning the value of that row to this var underscore r, that's this weird record type. And for each of those rows, we're going to iterate through these statements. So the body of this for loop is literally delimited by the word loop and end loop. We'll see that that's kind of a common kind of syntax in pgSQL. Well, what are we going to do with this? Well, we're going to set the film title to be equal to the uppercase version of var_r.title. I'm just illustrating here that we can coerce the string to be all uppercase if we want. It doesn't have any particular purpose here. But you can see here how we access the individual columns within that single row that's being assigned to var underscore r as we iterate through. So just the dot syntax says, within this record type variable, give me the title column. And that, of course, corresponds to the fact that we've selected the title column in the underlying query. We're also going to set film release year equal to var_r dot release year. So again, we're just going back and referring to this column from the underlying query. And then we're going to return next. What that does is basically adds this result, this film title and film release year, to the result set that's going to be returned from this loop. Remember that we're returning a table up here, and these two column names that we gave for this temporary table that's going to be the return value from this function correspond to these two identifiers down here inside the loop to which we're assigning. So we could have a table that had 100 columns in it here, and we could assign values to all those columns by just using this syntax, giving a value to each of those columns as we go through the results of this select. In this particular case, we're grabbing all of those things, just doing a little processing to illustrate that we can do some. But of course, we could have conditional statements here. We could skip rows entirely by performing some kind of a calculation and a comparison to say, I don't want that one to come out of this function. So anything we could do in a normal normal programming language, whatever that means. Anything we could do in a programming language, we could do here inside of this function. Here I'm just kind of doing the minimum necessary to be able to retrieve the film's title and release year according to the parameters that were passed in. So let's take a look at how this works when we invoke it. Again, getFilm returns something of type table. So we are, again, not surprised to find it showing up in the from clause. And in this case, I'm looking for films whose title ends with ER, right? So the wildcard, any characters at all, and then an ER. And then in the year 2006. And you can see that all of the films are in that year and that they all end in ER. And furthermore, all the film titles are in uppercase. So that's the result of this little function that we called in here as we are assigning the values to each of the rows in turn for that return, or for the table that's returned by the function. And then I'm just using limit 10 to cut this off so that it fits on the slide. Again, the fact that we're doing all this additional weird work under the hood to get this particular sort of temporary table that's returned in a custom way from that getFilm function can be used just like an ordinary table. And again, the common theme throughout this section of the course is that it's tables all the way down. So the rest of the SQL machinery, the selecting and the froms and all that kind of stuff, are perfectly happy to operate on this kind of temporary table that was just ginned up by calling getFilm, and everything else behaves exactly the same way. So we've seen iteration. Let's take a look at conditionals. You notice that the conditional syntax, again, uses this kind of verbose syntax where it's a block structure. The generic block uses begin and end, but any more specific kinds of statements that have a block as their body have their own syntax for delimiting the end of the block. And let's just look inside this piece of code here, and then we'll look at the outside after we've talked about it a little bit. So you can see here I've got the begin and the end that delimit a block, kind of a top-level block, and then I've got three conditional statements that start with an if and they end with an end if. Start with an if, end in an end if. Start with an if, end in an end if. And all these guys are doing is just comparing two variables, A and B. If A is bigger than B, we're calling this function raise, which is like raise an alert or raise an alarm. It's often used to sort of report errors back, but in this case we're just illustrating that we might use it to send some output to the standard output. We're going to raise a notice that says A is greater than B if A is greater than B, or A is less than B, or A is equal to B, depending on which of these conditionals tests true. And we can see that in the output we get A is less than B. Now, where do A and B come from? Well, we'll take a little bit of a step up here and look for the declaration section of this outer block. And here we're declaring a variable called A, a variable called B, they're of type integer. And just like in most programming languages, we can give those variables an initial value if we choose to by just using the typical assignment operator. So I'm initializing A to 10 and B to 20, which is why this conditional tests true, and we see A is less than B, A is less than B coming out on the output. Now there's a little bit of difference here in that we are not defining a standalone function in this particular case. We're using another pgSQL keyword called do, and do takes as its body a string that should contain some pgSQL code. So the double dollar signs here, we're using dollar quoting and providing the do statement with this block of executable code. So you can think of this as an anonymous code block. The do is just saying, I want you to do something, and what I want you to do is defined by the code that's appearing between the dollar quoted delimiters. As you might expect, there's also else if and else syntax associated with the conditionals in pgSQL. So here's basically the same functionality, a little cleaner because there's only going to be one possible outcome. But you can see that it's if, then the conditional, then, and then the body of the if statement. Then there's an else if with another conditional and the body, and then an else with its own body, and then finally an end if at the end. So in these examples, I'm only showing a single statement in the body of these portions of the conditional, that can be an arbitrary number of statements. The content of this conditional, whether it's the if, the else if, or the else clause, can be an arbitrary block of statements. You don't need to use a separate begin-end pair at this outer level. You can just stack statements up inside of the body of each of these sections of the conditional, and that'll work just fine. The rest of this is exactly the same. We're using the do again and providing kind of a anonymous function that is called immediately. There is a case statement in pgPL/SQL. So here's a new function called getPriceSegment. And you can see here we're trying to segment the different DVDs according to whether they're like the mass market, the mainstream market, high-end, or unspecified, whatever those things might mean. But the idea here is we're basically going to take a film that has that ID, and what we're going to do is look up that film in the database, and then depending on the rental price for that particular film, we're going to give back one of those 4 strings. So here's the, well, we're going to declare some variables here. First of all, a value called rate. That is where we're going to store the rental rate. It's going to be a numeric value. And we're also going to have a variable called price segment that we're defining to be a varchar. And notice that this function returns a varchar that has that same maximum length. So it's kind of clear here what we're going to do is grab the rate from the database, use that rate information to figure out which price segment it is, and assign a string, going to fit in that varchar, that we're then going to return back to the caller. So 2 steps here essentially. We've first of all got this select statement, and we're going to select into rate the column called rental rate from the film table where the film ID matches this parameter. So that's pretty straightforward. When we finish this select statement, rate will have the value of that particular film's rental rate. Now we're going to use that variable in the case statement. So this syntax, we're just basically going to select the value that we're trying to test, the rate itself, and then here's the syntax: when, and then a value, then. So it's a when then. We're saying that when the rate itself is equal to 99 cents, then we're going to do this code, set the price segment equal to mass. On the other hand, if the rental rate is $2.99, then we're going to set the price segment to mainstream and so forth. And if we don't match anything, we can also have an else case. This is kind of like the default case in other programming languages like C, where if none of these values match the value of that variable, we'll take the else clause and assign the price segment value to be unspecified. Again, each of these things is setting the value of price segment to some string, and then when we've completed that case statement, at the end of the process, we're going to return the segment for that particular film ID. So as an example of how to invoke this, we're going to do select get price segment. Remember that this is just going to return a scalar value, so we're using it in the select clause itself. And I'm also, just to make the output a little prettier, aliasing this value, or this column that's going to be returned. Instead of it being called get price segment, I'm going to actually give it a string to say, hey, I want you to use price segment as the column name. So that's what we see in the output here, price segment from this literal, and then the value for film ID 123 must have been $4.99 because it assigned price segment to high end and then returned that down here, and we see in the output high end. Now this particular case statement uses a quite familiar type of syntax that's very similar to a C language switch statement, where we have the switch, and then there's a specific variable that we're going to compare against, and then we have multiple cases, including a possible default case that is going to just do a comparison between the control variable and the constants that are supplied with the cases. Same thing here. We've got a control variable, and then we have some constants that are associated with the different when-then clauses. We can also use a more flexible version of the case statement, where instead of doing a comparison against a constant, we can actually execute arbitrary comparison operations. So here's another example where we're doing a slightly different query, but basically the same idea. Notice one thing that's strange here is that the case statement doesn't have that control variable anymore, because we're going to use individual comparisons to test to see if we have a true or a false value in each of the when-then clauses. And the first one that tests true is going to be the one that's going to be executed. So if the total payment for this particular customer was greater than $200, the code here is what's going to execute. If that's false, we'll fall through to the next case, run its comparison. If that tests true, we'll do this piece of code. If none of the whens test true and we have an else clause, then the else is what's going to get executed. And in all of these cases, we're just assigning service level to some string and returning that back to the caller. So a similar kind of an idea, but it's sort of a syntactic sugar that makes it easy to write a bunch of if, else if, else if, else if, else clauses. So here's some examples of doing that. We're going to grab customer 148 and get the customer service level of customer 148, customer 178 similarly, and customer 81 similarly. I'm also just trying to illustrate here the use of the union keyword in the query, because all three of these queries are going to come back with a compatible result set, basically just two columns giving the actual number of the customer ID with a column name called customer, and then the result of calling get customer service on that same customer. I can union those together, and I end up with a single result set that has these headers corresponding to the alias that I set up in each of these select statements, and then the name of the function, and then the three values that get returned for the different service levels for those different customers. We can also do looping. We've talked about this a little bit already. This is just another example of that. We're going to basically give a parameter to our function that is going to tell us how many values are we going to output from a particular invocation of a query. This also illustrates their ability to set a default value for that parameter. So if we invoke this without passing a value for n, it's going to use it's going to use 10 for the value of n. And here's the same syntax we saw before. We've got for, and then the assignment to the control variable rec, which we've defined up here to be of type record, and then the loop end loop forms the body of the loop. And we're just going to select title from film, order by title, and just limit that to whatever n is. One other interesting thing here, I guess, is that the raise notice function here is taking a control string, essentially. This is kind of like the control string in a printf statement, where you can supply, %d to print an integer and %s to print a string, that kind of stuff. It's not quite as rich a syntax, but you can use a %sign, and what it'll do is it'll fish out the next value from a variable list of values that appear after that control string and replace it in that spot. So output from this guy, we're going to say, let's loop through the query 5 times, and you'll see we get these 5 instances of a notice being raised, and then the first 5 film titles in the database ordered by film title. Finally, we'll say a few things about cursors. The idea of a cursor is a mechanism for encapsulating a query that gives us access to each of the individual rows that are going to come back from that query and allow us to process them sort of one row at a time. One of the key features of cursors is that it allows us to handle very, very large result sets. So far, the select statements that we've been executing, we've been kind of thinking of them as kind of an atomic operation. We run that select and we get back a table as a result of that select. And if there's 1,000,000 rows that came back in that select, we're going to get 1,000,000 rows in the result set. Now, that's not always a super efficient way of handling a large quantity of data. If we want to process that information in order to filter it out or to aggregate data or do some other operation on that result set, it's sometimes more efficient to try to do that processing as part of a stored procedure where that can all take place on the server, as opposed to us getting back 1,000,000 rows in a result set that has to be transmitted across the network to our client, stored in client memory, iterated over on the client side. That might be a very inefficient way of doing that if we can do the processing on the server side. And a cursor is an abstraction that allows us to do those types of things. So when we're using a cursor, this is a very standard way of approaching it. First of all, we're going to declare the cursor that basically says, here's what I want you to go get from the database. We're going to open the cursor, which basically says, okay, start fetching that information across. And then we're going to grab individual rows from that result set kind of on the fly. We aren't going to necessarily get all 1,000,000 rows. We might get just one at a time, and conceptually that's what we do. The database is probably going to do some amount of buffering and other things behind the scenes to improve efficiency, but conceptually we're only getting one row at a time. And we can kind of continue to iterate over those rows until we run out. So there's a tight loop going on here. And then when we're done, we can close the cursor and return the result set back to our caller. Could be a result set, could be a scalar, could be some other value that we're sending back as well. So let's look at an example of this. We're going to declare a function called getFilmTitles, and we're going to pass in a particular year. So again, using that p underscore as the prefix to indicate a parameter. And what we're going to do is return text. Now this seems like a little weird thing, but just to illustrate some other operations that we can do inside of pgSQL, I'm just going to give you back text. So maybe we want to create a comma-separated values list of things or something like that. At any rate, we're going to have a collection of variables here. So titles, it turns out that titles is what's actually going to be returned by this function. We can just kind of scooch down to the end here and see return titles. That's what's going to come back as that text that we're returning. So we declared titles to be of type text and given it a default value. Could also have just assigned that to be an empty string. We're going to use this record type in order to move our way through the result set using the cursor. So every time we go fetch a new row from the query, we're going to assign a new value to that rec film record. Now we're finally to the point where we're going to declare the cursor. So that's step one here. Cur films, so cur again, not current, but cursor for the films query is going to be defined to be a cursor, and that cursor is going to get a parameter passed into it, and that will allow us to use that parameter inside the query. So it's a cursor for, rather than saying as like they usually do in SQL for this kind of a delimiter, they say for. It's basically representing the result set that's coming back from this underlying select statement. We're going to do select star from film where the release year matches that p underscore year. So that p underscore year is basically that value, and that value is going to be coming from the parameter that we pass into this function. So at this point, we've defined the cursor. We actually haven't gone out to the database and started fishing the data into memory so that we can process. We've just created that cursor, and it's now ready to go. So the second step, back here again, is to open the cursor, and we're doing that here at line 11. We just say open cur films, and now we're finally passing in the value from here that's going to be sent into the cursor here so that the query is going to return rows that satisfy this where clause using that parameter. Okay, now we've opened the cursor. Presumably the database is going to do some things behind the scenes to start fetching the rows that satisfy this select statement. But now we have to enter a loop. So here we're doing a loop and an end loop. Note that this is not a for loop like we've seen before. This is just a loop. So it might look to you like, well, this is just an infinite loop that's going to continue to iterate here. We'll see that that's not the case. But what we want to do is loop over all of the rows that are going to come back as a result of invoking or of opening that cursor. So the third step here, fetch rows from the result set into the target variable. That's what's going on here in the statement at line 13. It's a fetch. So we're fetching from cur films, that's the name of the cursor, and we're fetching a single row from that cur films cursor into rec film. Okay, that's going to get one row from the select query underlying that cursor and assigned it to rec film. Now we can operate on that, do stuff with it. However, the next thing we're going to check here is if the fetch operation resulted in the end of the data. If we tried to fetch sort of one row past the last row that was actually returned by this underlying query, we want to know about that. We don't want to try to process a bogus row. So we're going to also do a test here to see if it's time to exit the loop. So that was step 4 here. Do we have more rows? We're going to say I want to exit the loop when the not found criterion has been met. And so basically if this fetch comes back and tells the stored procedure, hey, I was able to do a fetch, but it turns out that we've now exhausted all the rows in that cursor, this will test true and will exit the innermost enclosing loop, right? So that's going to cause us to come down here. We're then going to do the final step on the cursor, which is to close the cursor, and then return the value that we're building up inside this loop. So that's kind of the last piece here. If we do, in fact, have a valid row, in other words, if this exit clause didn't get hit, then what we're going to do in the logic of our super sophisticated stored procedure is check to see if the title column of the current record matches %FUL%. So any title that has FUL in it someplace is going to cause this conditional to test true. And then what we're going to do is we're going to append some information to the current value of the titles variable. So I'm going to set titles to be equal to its old value, and this double bar is concatenation. So we're going to say take titles, concatenate a comma, and then the title of the film, and then a colon, and then the release year of the film. And again, we can refer to the particular columns inside of this record that are being fetched from the cursor every time we iterate through this loop. So what we get in the output here, obviously I'm not showing the whole thing, but you can see here I've got gross wonderful 2006, day unfaithful 2006, reap unfaithful 2006. And you can see that I'm basically just pasting together with commas and colons the values that are coming back when I hit this particular query. So again, that's being created by this sort of long, painful string concatenation thing. Again, this isn't something you're probably going to want to do in practice. I'm just kind of giving you some examples that show various pieces of syntax that are used commonly. The key idea here is this notion of a cursor. If I want to do sort of iterative processing over the results of usually a large query is where you're going to trot this out, so that I can do a lot of processing on the server side and only return back to my client the information that the client really needs based on whatever processing I do inside the main loop. This is the approach that you should choose. And then finally, here's some additional resources that will be available to you if you download the slide deck.